Hello everyone and welcome to another video of Vivek Learns. In the last video that we had made of PepCoding Recursion, we had revised few of the questions that we had done earlier. So we had revised this print decreasing, print increasing function, this factorial function, then the power and the optimized power questions. So in the factorial question, we had discussed that we could perform this operation in a kind of more optimized manner also. So in this video, let's discuss how we can perform it in a more optimized manner. So let's set the faith expectation and meet the faith from the expectation. So we had this fact 3 which gave us 3 times 2 times 1 and fact 2 which gave us 2 times 1. And the general format that we had seen was n into fact of n minus 1. So the problem with this was every we were executing some instructions like this specifically when we are moving down the stack. So we have to traverse up the stack first, and then while traversing down the stack we mm, execute this. So what I'm thinking now is that we can have some more parameter, one more parameter. Let's say previous fact. So if I have, let's say, previous fact first is 1. Okay, so let me think now. So if I have something like int, okay, let me not disturb this method, comment it, and let's have another code. And to call that, let's have another call from here. Okay, let's say we have int num n, and then we have int previous fact. So this previous fact which is present that we get from here, I'm thinking of passing it along. Okay, so this previous fact, okay, so let us think now. So we do fact n minus 1 comma previous fact, right? Then we pass the previous facts, and eventually n will become 0. And when n becomes 0, we can pass in the previous fact, or we can pass in 1. Okay, so let me comment this and have it here. Okay, so let's say we have that return statement int n minus 1, so n will keep decreasing, and previous fact is nothing but this, right? Okay, so we'll have to put some variable here. So how will it work? Let's think about that. N times previous fact, right? N times previous fact. So if we do something like this, what happens? Okay, let's say I have it in a variable. Let's try to evaluate it. Okay, let's have it missing a curly brace here. Let's have it in notepad once, and not notepad, but let's have it in paint once. We delete this. We have it here. And let's try to analyze this part. So we have a stack here. Then we have some lines here. Okay, so what will be the first call that will be made? So let's say n is 3, and what we do is that for um, each and every method call, we give not each and every method call. So at the start, we'll give the value as per fact as 1. So have to call with we'll have the call in the stack with 3 comma 1. Okay, so your n is 3 and previous fact is 1. So as soon as the first line gets executed, another call is made, and that call will will give us fact of what it will give, fact of 2 comma 2 comma previous fact was 1. And now hmm, so this is wrong, right? Let me have it here. Yeah, let me remove it. So so first the call will be made with 3 comma 1. So once the call comes here, what will be the call method that will be called? So it will be n minus 1, which is 2 comma, and n is 3 or 3 times 1. So 3 times 1 is 3. Okay, so that will be the method which will be called. So if we continue further, we'll have fact of 1 comma, then it will be 2 times 1, right? And then we'll have fact of 0, and then we'll have of 0 comma, we'll have n, right? N is 1 comma previous fact. Okay, so I'm not considering the previous fact. So the previous fact was 1 year, but it is 2 year, right? So not 2, but we'll check. So 1 comma previous fact will be 3 year. So n is 2 year, 2 times 3. Okay, and for 0 fact of 0, we'll get 1 times the previous fact, which is 6. Okay, and so if n reaches 0, what do? We return 1. So that is not what we want to return now. So we can return previous fact now. So while moving up, we have found another base case, right? And what we what we found that the value is present in previous fact. So let me return. What if we do previous fact? Previous fact. So if we do this, then yeah, so this 6 times 1 will give us. And if we had 2, then we would have stopped here. It's okay. So if we had 2, then we would have started the iteration from here, right? n minus 1 2. So 2, we would have gotten 1 comma 2 times 1, then 0 comma 1 times 2. Yeah, so that would be the right answer, and then we will have returned the previous fact. So let's consider the edge case now. So if n is 0, then we would have previous fact as 1, right? Yeah, so I think this will work. N minus 1 n times previous fact. So first we return n num first we pass the values num comma 1. So if I want to have the factorial of 3, it will be oh, sorry, my bad. We have to return previous fact, right? That's what we discussed here. But I didn't make the change in the code. Like we were returning previous fact. Let me execute it once more. For 5, it will be 120. Yeah. So the only advantage that we get in this approach is we don't have to traverse down the stack. We only have to traverse up the stack, right? So once this statement executed fact 3 times 1, then this will be eliminated, kind of, right? So if we have this fact value, um, this, instead of having it stored in a variable, we directly have the call here, then we don't have to remember this call. The stack doesn't have to remember this call. That's what I'm saying. So while traversing up itself, we would get the answer. Okay. So yeah, that was the kind of optimized solution. So we will get a more optimized solution once we remove this as well, because we are still getting an unoptimized solution because this gets executed and after that this. Yeah, so this will be the final solution that I would say, the optimized one. So after that we had solved this power question. So in the power question we can have a similar kind of variable extra parameter added and we can store the power in that. So you can take that as a homework and you can do that. But mm, but we would be adding more parameters to our method call. So that is one thing you might want to consider. Okay. So let's try to analyze the next questions that we had solved. The next question that we had done was the sprint zigzag. So in this question, what we did was, mm, we hadn't solved this question, but we had tried to analyze the solution of this question. So we had the solution of this question something like this. Okay, let me have the solution here in Notepad. So what we had seen. So we had seen the first observation that we had made were whatever. So if we have only one recursive call, then whatever statements are present above the recursive call, okay, so they will be executed when we are moving up the stack, and whatever instructions are present below the recursive call, they will be executed when we are moving down the stack. So that is why we had made the optimizations in the factorial question. So we wanted to move up the stack only, and we didn't want to go down the stack, right? So that is where we had made the optimization by adding an extra parameter. Okay. So let's consider the scenario where we have two recursive calls. So if we have two recursive calls, then we had gave this call the name left call and this call the name right call, right? So this is left call, this is right call. Okay, so once we have these calls, the area above the left call, it is called pre-area. The area in between the left call and right call, it is called the mid area. And the area between this is area after the after the right call is post area. So this is how we used to define the areas, and then what we used to do is we used to draw an Euler's diagram for this, and we used to trace these Euler's diagram. So we could have drawn the stack trees for this, and we could have solved this question in that manner also. But the Euler's diagram was a much better and a much easier approach that we found, right? So in the Euler's diagram, what we used to do, we used to take the value of n which is present. So if let's say n is 2, okay, so let me have it here. We delete this first. So let's say if n is, let me have is, so let's say if n is 2. So what we used to do, we used to have these branches here, right? We used to branch out like this, something like this. Yeah. And what we used to do for this area, it will be the pre-area for 2. This area, it will be pre-area for 1. And then this is the base case. So once we hit the base case, we hit the mid area that we have here. So this is mid area for 1 and this is post area for 2. So we are traversing up the stack here. Then again we are traversing up. Then we hit the base case. Then we traverse down the stack for a while. Then we hit then we execute instructions present in the mid area. Then we again traverse up the stack, hit the base case. Then we come to the post area and execute the instructions present in post area of 1. Okay. Then we execute instructions present in post area of 2. So after this, all the instructions of this method call must have been executed. Then we again traverse up, execute instructions in the pre area of 1, hit the base case, execute instructions in the mid area of 1, then again we traverse up, execute instructions present in post area of 1, and then this all the instructions of this method would have been completed. So we fall down the stack and then we come here and execute instructions present in post area of 2, right? So this is how we had done the analysis of this question. So you can revise the question once if you want by watching the YouTube video that we had made earlier. So once we did this, the next question that we solved was the Tower of Hanai question. So this was very kind of a practical question, practical scenario that we had done. So the question says that we had you know, 3 disks. So let me draw those 3 disks. So we had not 3 disks. Let me draw the. So we had 3 towers first. Okay. So this, let's say we have these 3 towers, and we had 3 disks on those towers, and the disks were placed in such a manner that the heavier disk was at the left, and the disk with the least weight, it was at the topmost position. So let's say the weight of this was 3, 2 and 1. Okay. So these are disks which are present. So this was the initial stage that we had, and the final stage that we had, the final expectation was that all these disks should be moved from tower. Let's say this was T1 tower, this is T2 tower, and this is T3 tower. So the final expectation was we had to move all these disks from T1 tower to the final expectation. Let me have it here, to T3 tower. So the expectation was something like this. Let me see if I can copy this. Not T3 tower, we had to move it to T2 tower, right? Let me select this, paste it, so it pastes here only. Never mind. Yeah. So this is the final state which is expected. So we used to call this tower as the source tower, this tower as the destination tower, and this tower as the helper tower for now. So how do we solve it recursively? Okay, so we had seen that we have to reduce the problem, is what the catch in trying to solve this recursive call type of recursive implementation problems that we have. So once we reduce, or we make the problem statement solve, then we can think about it, right? So what we did was we had set the expectation of this, like we want to move three disks from tower 1 to tower 2, and we had a set of instructions also associated with those, like there should be the high disk with high weight, it should not be kept about the disk with low weight and all those, right? So following those instructions which you can see also, let me show you those instructions. Yeah, so we have to move only one disk at a time, never place a smaller disk under a larger disk, and you can move a disk at the top only, right? So using these instructions we have to move the plates from T1 to T2. Okay, once we did that, what was the how did we solve this? So we had set the faith that we we reduce the problem. Okay, so we reduce the problem by saying that we set the faith that we, let's say we have these three towers. So we had set the faith that we already know how to have two disks move to tower 1, tower 3. Okay, so we already know the instructions to move three disks to tower 3. Okay, so this was the faith that we had. So we already know the instructions for this. And okay, so this is T2, right? Yeah. So we already know the instructions for this. And now what needs to be done from to meet to go from this faith to the expectation? So how do we get this faith? So for the first question that I faced, or the problem that I faced, was how do I get a particular faith? So you can have any faith, Okay, you can have any faith, but you have to just find a faith, or you have to improvise the faith accordingly so that you can go from faith to expectation. Okay, so I could see that I am reducing the problem. So for while establishing the faith, make sure that you reduce the problem statement that you have. So you were given three disks, but you are thinking only about two disks now. So you had to print numbers from 1 to 10, but you reduce the problem, and you set the faith that you already know how to print from 1 to 9. Okay, so reducing the problem is the key role in setting the faith. So once you set the faith, how do you go from faith to the expectations? So we can go from faith to the expectations by printing the following lines. So we can have the disks. Okay, so we print, how do we print the instructions? I forgot. Okay, so this will be the weight of the disks and this will be the towers, right? Weight of the disk is, so what I'll do, I will move the disk with weight 3, which is present here, to from tower 1 to to tower 2. So once I do this, the next steps will be moving these disks which are present here to T2. So we already know the instructions for these, right? So we know the instructions for moving two disks from T1 to T3. So we'll use the same formula and move those disks from T3 to T2. Okay. So this is the only line that we had in that question. Okay. And then we made the recursive calls. We'll had we'll we had two recursive calls in that. So this was from moving from source to helper. So what this instruction will do is it will move the disks, the two disks which are present from T1 to T3, and we set the expectation that we already know that, and then we moved one disk which was of the highest weight 3 from T1 to T2, which is from source to helper, source to the destination, sorry, my bad, not the helper. So move this disk from source to the destination. And then what we did was, once we got that stage, when we had the largest disk here, we copied, we all, we have to move these two disks to T3. So this will be kind of moving two disks from T3 to T1. Okay. So we had wrote the instructions of moving disk minus ones from, so the source will be the helper here. Okay. The source is T3, from T3 to T2. So from T3 to T2 using source. And how did we identify the base case? We identified the base case when the disks are 0, what do we have to do? What instructions do we need to print? So identifying the base case is also an important thing which we have to learn. So we learned here that if disks are 0, we have to print no statements, right? Yeah. So this was a question similar to the print zigzag question that we had. This question. So here we have the left call and the right call, but we have only the instructions present in the mid area. So we had drawn the Euler's diagram for this as well, and then we traced the Euler's diagram. And whatever instructions like this statement was printed when we are present in the mid area. Okay. So that is how we had solved this introduction to recursion module last problem, which was Tower of Hanai. Then we moved on to the next module, which was recursion in arrays. So in the next video, we'll try to revise how we had solved all these questions in recursion of arrays. So that's all for this video. See you guys in the next one. Thank you.